Thank you for the introduction. I'm here to present my paper, Design and Implementation of Collagen-Based Relative Humidity Sensors. The motivation behind this work is to assert the utility of collagen as an inexpensive alternative for more traditional dielectric sensing materials in relative humidity sensors, specifically in health monitoring applications. First, I'm going to talk about relative humidity sensors, just generally how they work. Then I'm going to talk about collagen as a sensing dielectric. Then I'm going to talk about the device fabrication and our testing and results. So you're all sensors guys, you know that these are the metrics by which we can measure the performance of our sensors. So sensitivity, response time, linearity, hysteresis, and cross sensitivity are the main things we looked at, and we have to create trade-offs between cost, scalability, and power consumption. And this optimization is determined by the sensing mechanism used, materials, and the interface circuitry. So sensing mechanisms out there for relative humidity sensors are resistive, capacitive, mass sensitive, optical, and thermal. Resistive and capacitive are by far the most used, and we decided to go with a capacitive sensor. The geometry of our sensor is a coplanar interdigital electrodes. It's very simple to make, and the signal conditioning circuitry has been well established in industry. Also, capacitive sensors offer low response time, high linearity, and generally low cross sensitivity. So the way capacitive sensors work are you have two electrode plates with a dielectric in between. The dielectric absorbs water from the environment, hopefully proportionally, and then that causes capacitance changes due to the differences in the electric permittivity. So there are two main types of sensing materials, porous metal oxides and hydrophilic polymers. We're going with a hydrophilic polymer because the linearity is pretty high and hysteresis can be low if you have weakly polar sites in the polymer. So that brings us to collagen. Collagen, it makes up about 30% of the protein in animals. So due to animal agriculture, there's an abundance of collagen in the market that can be attained cheaply. And so the primary structure of collagen follows a repeating glycine amino acid. Every 3 amino acids is glycine. And most typically, the other 2 amino acids are proline and hydroxyproline. This structure creates polyproline 2 helices, and then those helices pack together into a right-hand triple helix called triple collagen. When the collagen packs together, it creates these fibers, and this is the main reason why we wanted to investigate collagen. That's because the fibers mean that it's a naturally porous material, and porous materials have greater surface area for your water to bond to. Also, the proline and hydroxyproline create polar regions in the helix, which is where the water will loosely bond. So we use a very simple fabrication steps to create our coplanar interdigital capacitors. We use thermal PVD to put a copper layer on our substrate. It's about 100 nanometers thick. Then we use positive photoresist with chemical wet etch to pattern the copper. And before we strip the photoresist, we spin the gelatin layer, and then we strip the photoresist with acetone, and that causes an afterimage of gelatin to be patterned between the electrodes. Now, I'm talking about gelatin, and I introduce collagen. Well, gelatin is denatured collagen. When it's hydrated at room temperature, it'll create some of those tropocollagen macrostructures that we need for the humidity sensing. And we use gelatin for this study because it is reliable and readily available. So that's an SEM picture of our device. The electrodes, like I said, were 100 nanometers thick. The gaps between the electrodes range between 10 microns and 100 microns, so these are fairly large devices. And the pattern gelatin is about 300 nanometers. So we used a controlled relative humidity chamber to test our devices. We have a commercial temperature and humidity sensor as a reference, and we also record the capacitance using a digital LCR meter. So to run the test, we put the device in the chamber at 50% RH and then 75% relative humidity. We did that cycle twice at 30 degrees Celsius, and then we repeated that at 35 degrees Celsius and 40 degrees Celsius. This is because the temperature changes is because we wanted to look at the cross-sensitivity of gelatin to temperature when used as a humidity sensing dielectric. So this is the time domain response of our devices. In green is, you can see the relative humidity in the chamber measured by the reference sensor. In blue, you can see the capacitance. And at about, you can also tell where the temperature shifts are because the capacitance just go wild at those points. And we wanted to look at the response time, but our data logger only samples at a rate of about 1 hertz, so that didn't really give us any meaningful data. You can see in this sort of zoomed in window that the humidity oscillates. That's because the relative humidity chamber is sort of tiling a wet bulb to keep the humidity almost correct. So the cross sensitivity to temperature is apparent in our devices. There's the same time domain plot except with the color bar showing the temperature. And I separated the data into by temperature, the 3 plots on the right, and you can see that there's a linear range and then a massive exponential range. And one of the things that you can notice from this is that the linear range increases as the temperature increases, but the effects of temperature on like hysteresis are much greater. So we wanted to zoom in onto the just the linear range of the devices, and it's clear that at higher temperatures the overall capacitance changes along with the sensitivity. So at 30 degrees C, the sensitivity is about 1.14 femtofarads per percent relative humidity, whereas at 40 C, the sensitivity is about 2.4 femtofarads per percent relative humidity. But one of the things that interests us in this plot is that as the temperature increases, at lower humidities, the variance is still less. So our future work is in determining the temperature sensitivity's dependence on relative humidity. Because if that's the case, then we can easily create, we can isolate the temperature effect using differential measurement. So in conclusion, we have established that capacitive coplanar interdigital relative humidity sensors are simple and inexpensive to fabricate. Collagen is a naturally porous material, and it has weakly polar side groups, which makes it a possible candidate as a dielectric sensing material. And the temperature sensitivity of collagen-based sensors produces a significant amount of interference that should be considered for reasons. Thanks for your attention.